Yo, welcome to Physics with Vinay. Hi, I'm Vinopal and I'm back for the second lecture of Electrostatics in this crash course. So first off, we are going to start off with the concept of electric flux and Gauss law. Let's take a look. So electric flux is defined as integral E dot dA. So E here is the electric field whose flux we want to calculate, and dA vector is the area vector. So the way this area vector is defined, if I have any surface, I can imagine it to be made up of lots of infinitesimal elements, and each element has its area vector whose direction is perpendicular to the element, and the magnitude of the area vector is equal to the area itself. Now for an open surface, you have two choices of the area vector. You could have chosen the area vector in two possible directions, and that is our choice. So usually in questions, if they ask you to calculate the flux through an open surface, usually they will expect you to give a positive answer. But for a closed surface, the convention is, if it's a closed surface, the convention is that the area vector is always chosen in the outward direction, never in the inward direction. That is the convention. So for a closed surface, if the question asks you to calculate the flux, you have to stick to this convention, and the answer for the flux may be positive or negative. So let's do a question, an example where we'll calculate flux. So let's say I have a surface parallel to the YZ plane. This is a square surface, let's say. This is A, 0, 0. This is A, 0, A. This would be A, A. So you should be able to see that this represents a surface that is parallel to the YZ plane and of side A. It's a square surface. So this is my electric field vector. You can see it's dependent on the XY coordinates. It's a variable. Another question is asking us to find the flux through this surface. So first of all, I'll consider the surface to be made up of elements, and the element should be chosen in such a manner that over that element the electric field is uniform. So in this electric field, you should see that there is no dependence on the Z coordinate. So therefore, let me select elements which are parallel to the Z axis. So that will ensure that along this element, the electric field is uniform. Now this will have a dA vector parallel to the x-axis, and therefore when I write my flux as integral E dot dA, I'll end up with E naught y by A dA. Just the x component of the electric field will appear in the dot product. And what can I write dA as? So let's say the y coordinate of the element is y, and therefore the thickness would be dy, and therefore the element, you should be able to see, I can write dA as A dy. So therefore this will become E naught y by A dy, and the y coordinate will go from 0 to A, and thus we will end up with E naught A squared by 2, and that is your electric flux. So I hope you've understood how we considered the element and how we took the dot product between the electric field and the area vector in order to calculate the electric flux. Now let's talk a little bit about solid angle. So if I have a sphere, we'd find the solid angle here as the area of that spherical cap divided by r square, where r is the radius of the sphere. So this is the definition of the solid angle. If I know the half angle, let's say alpha, subtended by that spherical cap, this comes out to be 2 pi into 1 minus cos alpha. So that's the relation between the solid angle and the plane angle. So this is a useful relation that you should remember. In general, if you want to calculate the solid angle due to an infinitesimal element, so let's say this is an infinitesimal element, and I want to calculate the solid angle subtended here. So let's say this is dA and this is r. So the solid angle here, d omega, comes out to be not dA by r square. You need to take the component of dA, let's say this angle is theta, along r vector. So dA vector, component of dA vector along r vector. So that will be dA cos theta. That is the definition of the solid angle. In the sphere case, every dA element, dA vector, is parallel to r vector itself, because dA vector will be normal to the surface, which will be along the radius. Now, a couple of properties of closed surfaces. So for a closed surface, any closed surface at an interior point will subtend a solid angle of 4 pi at any interior point, and 0 solid angle at an exterior point. So this is something that we should remember. Now, if I want to calculate the flux by a point charge through any surface, so suppose I have some surface and I want to calculate the flux by this point charge through this surface, so that flux comes out to be so you can imagine this formula physically also, you don't have to actually remember it. What we would like to remember is that the flux emitted by the charge in all directions, basically in 4 pi solid angle, is going to be q by epsilon naught. So in 4 pi, the flux is q by epsilon naught. So just use the unitary method. So therefore, in a solid angle of omega, what will be the flux? The flux would be q by epsilon naught times omega by 4 pi. And that's how you can remember this formula. It's a useful formula to calculate the flux due to a point charge. And finally, Gauss Law. So Gauss Law is basically just a statement of what we have written here. Integral E dot dA. So the circle in the integral just represents that we are talking about a closed surface, should be equal to charge enclosed by epsilon naught. So charge enclosed means is the total charge enclosed within the surface. The electric field here is the net field due to all charges. And this makes sense because through a closed surface, we already saw that the solid angle subtended at the interior is 4 pi. So if a charge is inside the closed surface, the entire q by epsilon naught will be going through the surface. And if the charge is outside, then the solid angle subtended at that point is 0. So the flux will be 0. So the only charges whose flux will appear are the ones that are enclosed within the closed surface. Let's look at an example where the question can ask you to calculate the flux through some surfaces. So let's start off with a cube. And I have a charge placed symmetrically at the center. So if the side length is A, the charge will be placed above the center of the base at a height of A by 2. So it's symmetrical to all the surfaces. Now, if I were to ask you to find the flux through one surface, so flux through the blue surface will be 1/6 of the flux through the cube, because the charge is symmetrically placed. So 1/6, and we know the flux through the cube or any closed surface would be q by epsilon naught. So that will be the flux to the blue surface. Suppose I were to divide the blue surface into 4 parts, and I ask you 4 equal parts, and I ask you flux to the green surface. The flux to the green surface would simply be 1/4 of the flux to the blue surface. So 1 by 24 q by epsilon naught. So in the question, they may not give you a cube and then ask you the question. They may just ask you, let's say a charge is placed here over a square surface, over the center of a square surface at a height a by 2. What is the flux to this blue surface? But that is just the situation that we discussed here. So here the flux will simply be 1/6 q by epsilon naught. Or they could ask you, we have a surface of side length A, and charge is also placed at a height over one of the corners at a height A, and what's the flux? Now this situation is exactly the flux through this green surface, because this green surface here has a side length of A by 2 and the charge is placed over one of the corners of the green surface also at a height of A by 2. So once again the flux here would be 1 by 24 q by epsilon naught. Let's say I have a isosceles triangle and I have a charge that is placed at a height A over one of the corners of the isosceles triangle. The question is asking us to find the flux through the triangle. Alright, so if you want, you can pause the video and give it a try and then take a look at my solution. Alright, so the way to do this, again, by recognizing symmetry, I can complete and form a square here of side length A by drawing another triangle, and my charge is also at a height of A over one of the corners, but that is nothing but the situation here, and because these two triangles are identical, the flux will simply get divided equally, and therefore the flux through each triangle will be 1/2 of the flux of this value. The flux through the triangle will be Q by 48 epsilon naught. I hope you've understood how we use symmetry in order to calculate flux. In all such questions, it is almost always the case of looking at the symmetry. So here I have a surface in the xz plane, and it is bounded by the x-axis and z equal to a, and going to infinity. So in this shaded portion, what is the flux by this point charge? The point charge is at a height a over the origin on the y-axis. So once again, think in terms of symmetry, and then you can take a look at my solution. Okay, so what I'm going to do here is I'm going to enclose the charge by a cuboid. So in all such questions, we'll try to enclose the charge by a closed surface, because through a closed surface, I know that the flux is Q by epsilon naught. Then I'll see some symmetry and try to figure out the flux through this surface given in the question. So I have my x-axis here, z, y. Let me form a cuboid, and my charge is kept symmetrically here. So this cuboid is going to infinity on both sides, and you should be able to see. Let me just label the corners A, B, C, D, E, F, G, H. So you should be able to see that E, F, G, H is in the xz plane. This entire thing is in the xz plane. So G, H would be 2a. The height is also 2a. So the charge is at a height of a over the origin. So it's symmetric with respect to the cuboid. This length is a. This length will also be a. So I want to find the flux to this surface. Now, first thing to note is that the flux through A, B, F, E and the flux through C, G, H, D. So basically these surfaces that are at infinity, the flux to those surfaces will be 0 because they have a finite area, but they are at infinite distance from the point charge, and we know that the field of a point charge goes to 0 at infinity. So the flux to those two surfaces will be 0. And the other four surfaces of this big cuboid, they are all symmetrical with respect to the charge. So by that I mean flux through A, D, H, E, flux through A, B, C, D, flux through B, C, G, F, and flux through E, F, G, H. All of these fluxes are equal, and therefore that will be 1/4 of the total flux to the closed surface, which is Q by epsilon. So this will be Q by 4 epsilon naught. Now, if I look at EFGH, so EFGH is itself divided into 4 parts, of which one part is the surface given in the question, and therefore flux to this part would simply be 1/4 of the flux through entire EFGH. So that will be Q by 16 epsilon naught, and that is your answer. So I hope you've understood once again how we use symmetry in order to calculate the flux. In all such questions, you should try and enclose the charge using a closed surface, because through a closed surface we know Q by epsilon. Then look at each surface of the closed figure that you've drawn, and then see how you can use symmetry to eliminate or to calculate the flux. Now let's look at a question which involves a line charge. So suppose I have a line charge, infinite line wire. But let me say that this line charge is, let me color it red, and in front of it I have a sheet symmetrically placed that is subtending an angle of theta. This is a rectangular sheet subtending an angle theta, and it's symmetrically placed. So if I look at the top view, so this red dot represents the line wire, and the straight line will be the top of the rectangular surface. and it's symmetrically placed. So these two halves of the blue line are equal, and this angle is theta. So the question is asking us to find the flux through the rectangular sheet. So lambda is the charge per unit length for the line wire, and let's say the height of the sheet is L. Alright, so in terms of these, go ahead and find the flux through the sheet. You can take it in terms of symmetry, try and enclose the line wire using a symmetrical figure, then you can take a look at my solution. Alright, so the one surface that is symmetrical with respect to this line wire would be a cylinder. So let me just draw a cylinder of height L. Now one thing that we must realize is that electric flux is a measure of the electric field lines cutting a surface. More the number of field lines cutting a surface, more the flux through that surface will be. So if I were to draw the cylinder in such a manner such that it's enclosing the blue surface. If I look at the top view, and if I look at this red portion of the cylinder, the field lines will be radial in the top view. So you should be able to see that all the field lines going through the blue surface will also be going through the red portion of the cylinder, and therefore the flux through the blue surface and the flux through this red portion of the cylinder are going to be equal. And now the reason I drew this cylinder is because with respect to the cylinder, the situation is symmetrical, and therefore I know that through the entire cylinder, because the flux is going to be Q by epsilon naught, I can very easily find out using unitary method the flux through a portion of the cylinder. So this entire cylinder, my flux is Q by epsilon naught, so basically entire 2 pi angle. So what will be the flux in this theta angle? It's very straightforward. The flux will simply be theta by 2 pi times Q by epsilon naught. So what is Q? Lambda times L. L is the length of the cylinder. So that is the charge enclosed within the cylinder. So I hope you've understood how we created a symmetrical situation where we compared the flux through the blue surface with the flux through a portion of the cylinder. Now let's look at a question where we are asked to calculate the force between a point charge and a surface, and we can use flux to make the calculations very easy. So suppose I have a square surface of side A and I have a charge placed symmetrically at a height A by 2, and I want to calculate the force between the square surface which is charged. So let's say it's uniformly charged and the charge is surface charge density is sigma. So I want to find the force between the plate and the point charge Q. So the way to do this kind of a question is, suppose I take an element here, and let's say the electric field due to the point charge is E at this point. So electric field would be this way. From symmetry, because the charge is placed over the center of the square plate, you should be able to see that the net force would be perpendicular to the square plate. That is just by symmetry. So let's say that the angle that the electric field is making with the normal is theta. So therefore my force would be the charge dq on the of the element. So let me just write dq directly at sigma dA, sigma times the element area, charge times the electric field due to the point charge times cos theta, because we know that the net force is along the normal. So this will be my net force. But here you should be able to recognize that because sigma is uniform, I can take it out of the integral, and this is nothing but E dA cos theta, basically E dot dA, and that is nothing but flux of the point charge through the plate. And we already know that. This was the first example that we did. Nothing but Q by 6 epsilon naught. So that's the force on the plate, and you can see this is a very beautiful method to do it without any need for actual integration. Similarly, if I were to go to the previous problem, and suppose I ask you here, find the force on the square on the rectangular sheet. Let's say this is given to be B, the width of the sheet here. and let's say the charge per unit area is sigma, once again uniformly charged. Once again, it's very simple. The force by symmetry is going to be along the normal. So we'll do the same calculation that we did on the previous in the previous example, and we'll get forces like we got here, and get the forces sigma times the flux through the sheet. So flux through the sheet is going to be that's it. So you don't even actually need this width. You see, it comes out to be independent of this width B. So I hope you've understood how we can solve such kind of force questions very easily without any need for actual integration. Now let's do an interesting question. Suppose I have a 2q charge here and a minus q charge here, and there's a field line that is going from 2q to minus q. So let's say this angle is alpha. So I want to find the maximum possible value of alpha. Maximum value of the angle that the field line makes, that field line is such that it starts from 2q and ends at minus q. Now because these charges do not have the same magnitude, not all the field lines from 2q are going to end up at minus q. So think in terms of flux, give it a try, and then you can take a look at my solution. Alright, so what I'm going to do is I'm going to first label this angle as beta here, and I'm going to draw another equivalent symmetrical line below, also at alpha, and this is beta. And now I can say, because electric field lines do not intersect, so I can say that all the flux being emitted by 2q in this region will enter minus q in this region, because all the other field lines within these two red lines which are coming out of 2q will have to end up at minus q. There cannot be a field line coming out of 2q and then cutting across. That is not possible. So any field line that is coming out between the two red lines has to end up at minus q, and therefore the flux emitted by 2q in this alpha region should be equal to the flux going into minus q in this beta region. So I know the flux emitted by a point charge is q by epsilon naught times omega by 4 pi. And what is omega? Omega is nothing but 2 pi into 1 minus cos alpha, where alpha is the half angle here. So this will become q by 2 epsilon naught into 1 minus cos alpha. So this is the flux emitted by a point charge. So coming to this question, the flux emitted by 2q would be 2q by 2 epsilon naught into 1 minus cos alpha should be equal to the flux entering minus q would be, the magnitude of the flux would be q by 2 epsilon naught into 1 minus cos beta. So therefore I'll have 1 minus cos alpha is 1 minus cos beta by 2. Now for the maximum value of alpha, I will need the maximum value of the left hand side, because cos alpha will decrease as alpha increases, and therefore I will need the maximum value of the right hand side. Now what is the maximum value of the right hand side? Beta can be any angle, remember, from 0 to 180 degrees. So can you see that the maximum value of the right hand side would be when beta is 180 degree. So when beta is 180 degree, I'll have 1 minus cos alpha is 1 by substituting cos beta as minus 1, and therefore alpha would come out to be 90 degrees. So if I were to just plot the electric field line 2q minus q, this field line at 90 degrees will basically be going to infinity, and then you can just imagine it will be looping up from infinity and coming here straight into minus q. Basically this will be 180 degrees. This is beta. And the other field lines, of course you'll have a symmetric field line below 2q as well. And the other field lines to the right of this 2q will be going into minus q. And these field lines will of course never reach minus q. So I hope you've understood how we plotted the field lines for 2q and minus q where the magnitude of the charges were not equal. Now let's come to sphere and its field and potential. So if I look at a hollow sphere uniformly charged, the field outside is kq by r squared, where q is the charge on the sphere, and the field inside is 0. So you can get this just by using Gauss law. And for a solid sphere, once again uniformly charged, electric field outside is kq by r squared, r greater than r, and inside is kqr by r cube. Q is the total charge, capital R is the radius. So in vector form I can write for r less than r, here you can put an equality sign anywhere, it doesn't matter. In vector form I can write E vector is kqr vector by r cube, and if I substitute k as 1 by 4 pi epsilon naught and q as rho into 4 by 3 pi r cube, you will get a very nice simple expression for the electric field inside the solid sphere, rho r by 3 epsilon naught. So you can choose to remember it however you like. Let's also talk about potential. For the hollow sphere, I am talking about hollow sphere, r greater than r, the potential is simply kq by r, and for r less than r, the potential will be a constant because the electric field is 0. So whatever the potential is on the surface will also be everywhere inside the hollow sphere. And for a solid sphere, r greater than r, once again kq by small r, and r less than r, you will have to integrate the electric field in order to get the potential, which comes out to be kq by 2r cube times 3r square minus r square. So this is the potential inside a solid sphere, uniformly charged solid sphere. If I were to just plot the potential for a solid sphere, you can see at r equal to 0, the potential is 3 kq by 2r, and it's a quadratic with a negative coefficient of small r squared. So the parabola will be mouth downwards up till r, and then greater than r, the potential is inversely proportional to smaller, so that will be a hyperbola. So this is the way the potential will look like for a uniformly charged sphere. If I look at field inside a cavity, so let's say I have a uniformly charged solid sphere and I have a spherical cavity inside. So let's say this is D vector. So D vector is the vector connecting the two centers, the center of the bigger sphere and the center of the cavity. So I want to find the field at any point, let's say point P inside the cavity. So what I can do is I can imagine this to be made up of the entire solid sphere minus the smaller sphere. So point P is, let's say here, let's say the vector from the center or the position vector from the center of point P is, let's say, r1 vector, and position vector of point P from the center of the cavity, let's say r2 vector. So I can write my electric field, we already saw we could write it as rho r by 3 epsilon naught. So this will be rho r1 by 3 epsilon minus rho r2 by 3 epsilon naught. We are basically subtracting the field due to the smaller sphere. And what is r1 minus r2? r1 minus r2 is nothing but D vector, you should be able to see that. This is r1 vector, this is r2 vector. So r1 minus r2 is nothing but D vector, so I'll have rho d by 3 epsilon naught. So this is a very nice result that the field inside a spherical cavity, inside a uniformly charged sphere, is uniform, it is parallel to D vector. At any point P, r1 minus r2 will result in D vector. So if this is D vector, the field lines are going to be looking like this, parallel to D vector. Let's also consider the case of a non-uniform sphere. Sometimes it comes in JEE where they ask you to find the field or potential due to a non-uniformly charged sphere. So let's take a look at an example. So let's say I have a sphere and the charge density is varying as rho naught r by capital R. So I want to find the field as a function of r. Alright, so for r less than r, what I'm going to do is I'm going to apply Gauss Law. So at a distance smaller, I'm going to consider a Gaussian surface, a spherical surface. So here, because charge density depends only on small r, the distance from the center, the electric field everywhere would be radial by symmetry. And the magnitude on that Gaussian surface will be equal, because the electric field will only depend on the distance small r. So I can write E into 4 pi r square. This is the flux through the Gaussian surface. Should be equal to charge enclosed. Charge enclosed inside this red Gaussian surface. Now, in order to calculate the charge enclosed, we'll have to do some integration. So let's say at a distance x, I consider a thin spherical shell whose thickness is dx. So can I write that the charge would be charge density into the volume of this thin blue shell, which will be area 4 pi x squared times the thickness dx. And all I have to do is integrate from 0 to r. We want the charge enclosed within that red surface of radius small r. So let's see what we get. So at a distance x, the charge density is going to be rho naught x by r. So we'll get a charge as r power 4 by 4. And let's just substitute this charge enclosed here, and therefore I get my electric field as rho naught r squared by 4 r epsilon naught. So this will be the electric field for r less than capital R. And what about r greater than capital R? For that situation, I'll have my Gaussian surface outside. Once again, I'll write E into 4 pi r squared is charge enclosed by epsilon naught. Now, charge enclosed will basically mean the entire charge of this solid sphere. So, in order to get the entire charge, I don't have to integrate again. I can just substitute small r as capital R here. So, just substitute small r as capital R, you will get the charge enclosed within the entire sphere, and therefore you will be able to calculate the electric field. So, I'll just write down the final expression. So rho r by 4 epsilon naught is what you will get your electric field as. Now you can just confirm that at small r equal to capital R, you should have the same electric field due to both expressions. Oh, this should be, this rho is actually rho naught. Now let's do a type of problem where you can use a very beautiful method to avoid integration. So whether it is electrostatics or gravitation or even magnetism, if the field is proportional to r vector, so let me just take the case of electrostatics for now. So suppose electric field is some c r vector, c is some constant, and you have a charge distribution which is uniformly charged. So I have uniform charge distribution. Let's say that charge density is rho. So if I want to calculate the force by this electric field on this charge, I can say the force would be integral dq E vector. Here, what is r vector? R vector may be any position vector from some origin. So I can write dq as rho into the volume dv times E vector. Let me write that as cr. So because it is uniformly charged, I can take rho and c also out of the integral. This will be r integral of r dv. This is what we will remain with. So now, in order to write down the integration of integral r dv, we want to avoid the actual integration. So because we can treat it as a uniform body, I should be able to write that integral r dv divided by volume, the total volume, should be equal to integral r dm divided by total mass. What have I done? I have multiplied numerator and denominator for this by the mass density. So if I just multiply the mass density on numerator and denominator, here rho is mass density, I will get my right hand side. And what is right hand side? That is nothing but the position of the center of mass. So basically I have that integral r dv divided by the volume is equal to the position of the center of mass. And therefore integral r dv will simply be rcm times the volume of the charge. So my force on such a uniform charge distribution will simply reduce to rho c times volume times RCM. So I hope you've understood how we completely avoided the actual integration, and you can even see what is this rho into volume. That is nothing but the total charge. Here rho is charge density. So I can write my charge density into volume as the total charge. And what is C times RCM? Can you see that is nothing but the electric field at the center of mass? So basically the force is simply the charge of the body times the electric field at the center of mass, and this happens when the electric field is proportional to r vector, which is a position vector. Now you may wonder where such a field will arise, where the field is proportional to r vector. In fact, it is a very common situation. Field is proportional to r vector inside a uniform solid sphere. Field is proportional to r vector inside a uniformly charged cylinder, a long cylinder. Same for gravitation. And instead of integrating every time, you can just use this final result. So let's take a look at a question where you can apply this. I'll go to the next page. Suppose I have a sphere, uniformly charged sphere. Charge is q, radius is r. It's a solid sphere. And the question is asking us find the force by 1/2 of the sphere on the other. So at a distance r, at a distance small r from the center, you should know by basic theory of Gauss law that the field there is kqr by r cube. Now this is proportional to r vector. K is 1/4 pi epsilon naught. And therefore my force by 1/2 on the other will simply be the field at the center of mass. So what is the center of mass of a hemisphere? Where is it? It is at 3r by 8. So the field at the center of mass would be kq by r cube times 3r by 8 multiplied by the charge of the hemisphere, which is q by 2. That's it. So you will get it as 3kq squared by 16r squared. So that's your force experienced by 1/2 of the sphere. Now let's come to cylinder. So I have a long cylinder. Let's say I have charge density as sigma on the surface. I'm considering a hollow cylinder, so the charge is only on the surface. So let's say this radius is capital R, and at a distance small r, for r greater than r, my electric field, if I want to calculate, I can just consider a Gaussian surface. So symmetrical surface would be a cylinder, let's say of length L. So the field will again be radial, so the flux will only be through the curved surface. So I can write E into 2 pi RL should be equal to the charge enclosed. So charge enclosed would be the entire charge on the cylinder of length L, this red cylinder. So that will be sigma times 2 pi capital RL, and therefore my electric field would be sigma R by epsilon naught, of course, sigma R by smaller epsilon naught. So this will be the field for outside the hollow cylinder. Now you don't have to actually remember this, but you should be able to derive it quickly in the exam using Gauss law. And what about inside? You can draw a similar Gaussian surface inside Gaussian cylinder, and you will see, of course, there's no charge inside the hollow cylinder, so the electric field would be 0. Similarly, if I consider a uniform solid cylinder, and this time I'll give you charge per unit volume density. So for R greater than capital R, once again consider a Gaussian surface, Gaussian cylinder of length L. So I'll have E into 2 pi RL should be equal to charge enclosed inside would be rho into pi capital R square L, because only this red portion of the solid cylinder times epsilon naught. So you can get your electric field. Once again, not something standard. So this is R greater than R. And for R less than R, we'll consider Gaussian surface inside. So I'll have E into 2 pi small RL again should be equal to charge enclosed here. So there will be density into pi small r square L by epsilon naught. This is for R less than R, and of course you can get the electric field once again. So this is how you get the electric field for a hollow as well as a solid cylinder. Let's come to a slab. So I have a long slab of charge. So this is infinite, but this thickness is finite. So let me just draw the front surface. Let me just mark it by blue. I'm just redrawing that blue surface. So I want to find the electric field at a distance x. So first let me consider x less than d by 2. So I've been given charge per unit volume is rho. So let me consider a Gaussian surface this way, symmetrical with respect to the axis. So x distance on both sides, and let's say this cross-sectional area of the Gaussian surface is A. Now by symmetry, my electric field will be normal to the slab because it is infinite upwards as well as downwards. So every point on the slab is like the midpoint. Every point here is like the midpoint of the surface. So electric field vector cannot have a component upwards or downwards because that will violate symmetry. So can I write my flux? Would be E times A area vector is outwards at both ends, so multiplied by 2. There will be no flux to the curved surface because electric field will be perpendicular to the curved surface area vector. This should be equal to the charge enclosed. So charge enclosed will be charge density multiplied by the total volume. So the length is 2x times area divided by epsilon naught. So my electric field inside the slab would be rho x by epsilon naught. What about the electric field outside? Very similar. So outside I'll consider again Gaussian surface symmetrically, whose length would be 2x. Let's say area is A. So I'll write the same equation. Only thing here is that the charge enclosed will only be inside the slab. So because this distance is d, I'll have rho d A divided by epsilon naught. This shaded portion is the volume of the charge. So this is x greater than d by 2. So my electric field would be rho d by 2 epsilon. It will be a uniform electric field outside the slab. So I hope you have understood how we can calculate the field to a slab, once again using Gauss law. Now let's look at the relation between charge density in terms of electric field. So if you're given electric field, how to calculate the charge density? So first let's take the case that if electric field is a function of the x coordinate, so one dimensional case, and I'm going to find the charge density in terms of this electric field. So this is known to us. What I'm going to do is, at a distance x, let me consider a Gaussian surface. So let's say this area is A, this area is also A. So in this Gaussian surface, I have my electric field, and the electric field here would be E plus D. So this is at x, and the right hand side is at x plus dx. Now my area vector for the left side would be to the left, and for the right side would be to the right, because remember area vector has to be always outwards for a closed surface, and so my net flux would be E plus dE times area minus E times area should be equal to charge enclosed. Charge enclosed in this volume would be rho times area times this is dx divided by epsilon naught. So I will get charge density as epsilon naught dE by dx. So this will be the charge density in terms of the electric field. So you can see for a uniform electric field you will have zero charge density because the derivative will be zero. Now in general, if I just define flux as the electric field times the area, if I look at this equation, that is nothing but d phi, the change in this quantity E times area. So in general I can write d phi is equal to rho A dx by epsilon naught. So rho would be epsilon naught by A d phi by dx. Now the reason I am writing it in this manner is because I can now use this expression to generalize it to a spherically symmetric case. If I have electric field as a function of R given to us, so this is in 3 dimension. R is basically the distance from the origin. So my Gaussian surface, you can imagine it will be spheres. And therefore, when I use this expression epsilon naught by A d phi by dx, so now instead of x I'll have d phi by dr. So epsilon by A, now A for area of the Gaussian surface would be 4 pi r squared. Derivative of the flux now will be E times 4 pi r squared. So this will come out to be epsilon naught by r squared, the derivative of E times r squared. So that will be the charge density in a spherically symmetric situation where the electric field is a function of the distance from the origin. So in such cases where you know the electric field is a function of r or as a function of x, you can calculate the charge density. We'll look at an example of this when we come to accelerated conductors later on in this chapter. And another application of this formula here is when you need to calculate the charge density in a dielectric, varying dielectric in capacitors. So we'll come to that later. Now let's come to the concept of self energy. So self energy is nothing but the potential energy of a system. So it's like the potential energy of the interaction between the constituents of the system itself. So for example, if I have 3 charges, let's say this is RA, RB, RC. So these are the distances between those two, between the pairs of charges. So if I want to write the self energy of the system, it's just the potential energy of all the interactions. So that will simply be K Q1 Q2 by RA plus K Q1 Q3 by RB plus K Q2 Q3 by RC. In general, we have an expression for the energy density is given by half epsilon naught T squared. So the electric energy density is given by half epsilon naught T squared. So basically this means that we can visualize the energy stored in the electric field. Wherever in space electric field is present, we can associate an energy density with that electric field at that point in space with a value of half epsilon naught T squared. Now for a uniform hollow sphere, we have the self energy as kq squared by 2r. So this hollow sphere charged with q, and for a uniform solid sphere, where the charge is distributed throughout the volume of the sphere, the self energy comes out to be 3kq squared by 5r. So these are values that you should remember, and you can derive it. One way to derive it, these energies, is using this energy density and integrating it over the entire space. Let's take a look at an example. So here the question says that I have a hollow sphere uniformly charged with charge small q and another charge of the same magnitude placed at the center of the hollow sphere. So the question is asking us find the energy required to compress the sphere to half its radius. Okay, so basically the energy required, the energy that we supply, will be the change in self energy of the system. Now here the self energy of the system is not just the self energy of the sphere, but also you need to include the interaction energy between the sphere and the point charge. So you can pause the video and give it a try, and then you can take a look at my solution. Alright, so the initial self energy for the sphere alone, it would be kq squared by 2r. Plus, what is the interaction energy between the sphere and the point charge? The potential due to the point charge at a distance r is kq by r times the charge of the sphere, so kq squared by r. So this will be 3 kq squared by 2r. So this is the interaction energy between the point charge and the sphere, and this is the self energy of the sphere. And the sum is the total self energy or the total potential energy of the entire system. And similarly, finally, the radius is just reduced to half its value. So the self energy would be kq squared by twice of r by 2 for the sphere, plus the interaction energy. Now the sphere and the point charge are at a distance of r by 2. So kq squared by r by 2 will be the interaction energy. So this will simply be 3 kq squared by r, and therefore the change in self energy would be, just subtract and you will get your answer. This is the energy required to compress the sphere. Physically, it means that the sphere is not only facing repulsion between the charges on the sphere itself, but also facing repulsion from the point charge at the center. Now let's talk about electrostatic pressure. So suppose I have a surface charge. So I have a surface charge, and just above it the electric field is E1, and just below it the electric field is E2. So the pressure here is given by half epsilon naught E1 squared minus E2 squared. So this is the pressure, the electrostatic pressure exerted on the surface charge. This formula for pressure is derived from basically applying Gauss law on a small section of the surface charge. Let's take a look at an example where this is going to be useful. So let's see. I have two concentric spheres. So let's say both of them are charged with charge q. Let's say this radius is r and this is 2r. These are hollow spheres and they are uniformly charged. So the question is asking us, find the force on one half of the bigger sphere, bigger spherical shell. So this blue section, on that what is the net force? That is what is being asked. So if I can get the pressure on the blue section, I can multiply it by the cross sectional area or by the projected area to get the force. So what will be the pressure? All I need to do is figure out what is the electric field just outside and just inside. So now that's very straightforward. So if you want, you can pause the video right now and calculate E1 and E2 and then use the pressure formula to get the force, and then you can take a look at my solution. Alright, so here E1 is going to be due to both the charges. So kq by 2r the whole squared plus kq by 2r the whole squared. This is due to both the spheres. Just outside the sphere, because the distance from the center is 2r. And just inside the bigger sphere will have zero electric field inside it. So the field E2 will only be due to the smaller sphere, and that will be kq by 2r the whole squared. And therefore, my pressure will be half epsilon naught E1 square minus E2 square. So just substitute E1 and E2 here, and you will get a pressure as half epsilon naught. So E1 is basically just kq by 2r square, and E2 is kq by 4r square. So this will be 3 by 16 k square q square by r power 4. And now that we've gotten the pressure, you can get the force as simply pressure times the projected area. So for this hemisphere, the projected area would be pi into 2r the whole square. So pi into 2r squared. So this will be the force, and you can do the calculation on your own. You can even substitute k here as 1 by 4 pi epsilon naught to simplify it. And basically this is the force for a uniform pressure. It's pressure times the projected area, something that you should have learnt in your fluid mechanics chapter. Now let's come to conductors, a very important part of electrostatics. So a conductor is something that has a large number of free electrons. And in this chapter, we are talking about the situation of equilibrium. There is no external voltage supply, so there is no current going on in this chapter. We are going to talk about equilibrium. So in equilibrium, the net force on the free electrons is 0. And here we neglect the gravity of the electrons, and that means that the only other force is the electric force. So the electric field itself is 0 inside the conductor. So when I say inside the conductor, that means inside the conducting material. Let's talk about some important properties of the conductor. So first property is that charge resides only on the surface of the conductor. Suppose I have a metal object, that means a conductor. So this is very easy to prove that if I just consider a Gaussian surface here, consider any Gaussian surface, because the electric field is 0 everywhere inside the conducting material, that means charge enclosed should be 0. So you can just make as many number of Gaussian surfaces you want inside the conducting material and prove that charge everywhere is 0 inside. The only place where the charge can reside is the surface. So if you were to put some external charge on this metal object, that charge will spread out on the surface. In the presence of a cavity, if I have a conducting material in which there is a cavity, so this is a cavity, and the shaded portion is the conducting material. Now if I were to place a charge inside the cavity, what will happen is it will attract electrons from the conducting material, and therefore you will have negative charges. If the point charge is positive that I have placed inside the cavity, then you will have negative charges that will be induced on the inner surface of the conductor, so the inner surface of the cavity. Now this word induced sometimes causes confusion in students, because that word makes it feel like they're appearing on their own, but that's not the case. Charge is always conserved. So when we say that charge is induced on the inner surface of the cavity, it just means that charge is traveling from the bulk, from the volume of the conductor. The charges are coming, the electrons are coming, and then residing on the inner surface of the cavity. So that means that if it's a neutral conductor, there will be positive charges left on the outer surface. So now it's very easy to show that if you consider a Gaussian surface enclosing the cavity, because the electric field has to be 0 at all points on the Gaussian surface, because we've taken it inside the conducting material, the total charge enclosed also has to be 0. And therefore, the total charge that will appear on the inner surface of the cavity will simply be negative of the charge that you have placed inside the cavity. So minus q will be induced on the inner surface. Once again, the Gaussian surface that is enclosing the cavity must have total 0 charge enclosed because of the 0 electric field. And if the conductor is neutral, if the conducting material is neutral, and if minus q is appearing on the inner surface, and we already saw that charge can only reside on the surface of the conductor. So the conductor here has two surfaces, inner as well as outer. So therefore, for a neutral conductor, you can see that plus q charge will appear on the outer surface. A total charge of plus q will appear on the outer surface just by charge conservation. Total charge of the conducting material should be 0 if it's a neutral conductor, and the conducting material here is the red shaded portion. Now let's look at the distribution of charges. So suppose I have a conductor with a cavity, and if I place a point charge here, let's say I put 2q charge on the conducting material as well. So the conductor is not neutral anymore. This red shaded portion is the conducting material, that is not neutral. So how will the charge get distributed? So minus q will appear on the inner surface of the cavity, and because the conducting material itself has a total charge of 2q, therefore the outer surface should have a total charge of 3q. So that 3q and minus q will result in 2q. The charge of the conducting material is conserved. And what about the distribution? The distribution will be non-uniform because of the random shape of the conductor. So in general, we will say that the distribution is non-uniform. Only if the surface was a sphere, then we can say that the distribution will be uniform. I'll look at that example right now. So suppose I have a spherical surface. I have a random shaped cavity here. So once again, the conducting material is this red shaded portion, and I have a point charge placed. 2q charge is placed on the conductor. So minus q will appear on the inner surface. Now because the cavity shape is not sphere, it's random, so that will be non-uniform. And the charge on the outer surface now the outer surface is a sphere. So charge on that outer surface will be uniformly distributed. And how much charge would that be? That would be 3q. If I look at another example, let's say I have a spherical conductor with a spherical cavity. Now I place a charge off center, so it's not at the center of the cavity. Let's say this conductor is neutral. So because the point charge is not placed at the center of the cavity, you can imagine that it will attract more electrons from the left hand side of the cavity than the right hand side. And of course, positive charge will reside on the outer surface. Because the conductor is neutral, the total charge should be 0. So inner surface would be minus q and outer surface would be plus q. So this minus q will be non-uniformly distributed. I'm just using shorthand NU for non-uniform. And plus q on the outer surface would be uniformly distributed because the surface is spherical. Here, if I were to place another point charge, let's say q dash or any other external charge, then the outer surface charge will become non-uniform because of the presence of the point charge. So one thing we should know is the concept of electrostatic shielding. That is exactly what is happening here. The field lines, due to the charges inside the cavity, they do not come out. So they do not affect the outer surface or they do not affect q dash. And that is why in the absence of q dash, the outer surface charge will be uniformly distributed because there is no effect of the location or the charge of q and minus q on the outer surface. The only thing that can affect the outer surface is any external charge placed. So if I were to just talk about that in more detail, so I have my conducting material, the red shaded portion. I have a cavity. Let's say I have a charge q. Let's say I have a charge q dash. So minus q will appear on the inner surface of the cavity, and the field lines will be going from the point charge to the inner surface, and they'll all be perpendicular. So the field is always perpendicular on the surface of a conductor, and the reason is because the conductor has zero field everywhere inside. It is equipotential, and we know that electric field lines are perpendicular to equipotential surfaces. So the surface of a conductor is equipotential. So the entire conductor is equipotential and the field lines are going to be perpendicular to the surface of the conductor. So let me just draw these field lines in blue. So these blue field lines are produced due to the charges inside the cavity and on the inner surface of the cavity. So these blue field lines do not come out. So what does that mean? That means that the electric field due to Q and minus Q is 0 everywhere outside the cavity. Their field lines do not come out, and that is why they do not affect the outer surface charges or they do not affect any external charges. And there may be some charges on the outer surface that may be induced depending on whether the conductor is neutral or whether it had some charge originally. And the field lines due to the outer surface and Q dash, those field lines are represented by these green field lines. They do not enter inside the conducting boundary. They do not enter inside the outer boundary. So mathematically that means that the electric field due to outer surface plus Q dash, the field lines due to outer surface as well as Q dash, is 0 everywhere inside the outer boundary. So in this entire region, the field is 0 due to the outer surface and Q dash. Now let's also talk about potential. The potential due to Qn minus Q. What can we say about that? We already know that the electric field due to Qn minus Q is 0 everywhere outside the cavity. So everywhere outside the cavity, if the field is 0, that means the potential due to Qn minus Q will be a constant. Now, can we say something about the value of the constant? Everywhere outside the cavity means all this region including infinity, and we know at infinity we have the convention that potential is 0. We choose that, and therefore potential due to Qn minus Q is 0 everywhere outside the cavity. So potential due to Q and minus Q is 0 everywhere outside the cavity. Now what about the potential due to the outer surface and Q dash? By the same logic, because there is the electric field lines of the outer surface and Q dash do not enter the outer boundary. So everywhere inside this outer boundary, the field is 0, therefore the potential should be a constant. The potential due to outer surface and Q dash is a constant inside the outer surface, inside the outer boundary of the conductor. However, we can't talk about the value of the constant, unlike in the case of Qn minus Q. In the case of Qn minus Q, infinity, we knew the potential there is 0. So everywhere the potential will be 0 outside cavity. Here, infinity is not part of the region here. The region is inside the outer boundary. So here the value of the constant will depend on the actual situation, the physical situation. How much charge is there on the conductor, where is the cavity located. So we'll look at a couple of examples on how to calculate that potential. Alright, so in this question we have a metal sphere of radius A, and we have a cavity whose center is at a distance of f from the center of the bigger sphere. And at the center of the cavity we have a point charge Q, and at a distance c from the center of the bigger sphere I have a point charge Q dash. So what is the question asking? The question is asking find the field at S due to the outer surface charges, find the field at S due to the inner surface charges, and find the field at point P. So here the red shaded portion is the conducting material. Alright, let's take a look at how we can go about solving this question. So first of all, we should recognize that at S the net field is 0 because it's inside the conducting material. Now, can I say that the field due to the outer surface plus the field due to Q dash is 0 at S? That's what we saw, that the field because of the outer surface charges and because of Q dash will result in 0 everywhere inside the outer boundary. Now we can't directly write the field due to the outer surface at S because we don't know its distribution. Because of the presence of Q dash, the charges appearing on outer surface will be non-uniformly distributed. So we don't know the distribution, we don't know how to calculate the field directly. However, we can use this fact and then say that the outer surface charge will produce a field equal to negative of that by Q dash. And the field by Q dash we know at S. The magnitude of the field by Q dash would be KQ dash divided by the distance here from S to Q dash. That will simply be C square plus D squared. So that will be the magnitude of the field of the outer surface charges, and of course the direction will be opposite to that produced by Q dash. Similarly, for the second part is the same logic. The field produced by the inner surface charges. So we'll have minus Q induced on the inner surface, and that distribution will be uniform because the charge Q is placed at the center of the spherical cavity. So here you can actually calculate the field due to the inner surface at S directly, because it is going to behave like a hollow sphere, uniformly charged hollow sphere. So I can just directly say that the field due to the inner surface would be KQ, magnitude would be KQ by R squared. So R is this length of this green arrow. So that will simply be F squared plus D squared. And of course the direction will be towards the center of the spherical cavity. And finally, what is the field at point P? At point P, there is no field produced by the outer surface and Q dash. So at point P, the only field that will be produced is by the point charge Q, and the inner surface will produce zero field because that is uniformly distributed, and we know that the field due to a uniformly charged hollow sphere is zero inside. So the field at point P will simply be due to the point charge Q at the center, and that's at a distance R, so that will simply be KQ by R squared. So I hope you understood how we were able to solve this question. Alright, let's take a look at another question, this time about potential. So I have a solid metal sphere inside which we have a cavity, spherical cavity. O is the center of the sphere, the bigger sphere of radius R, and C is the center of the cavity. And we have a point charge placed at a distance of R by 8 from the center of the cavity. The cavity itself has a radius of R by 4. So what is the question asking? The question is asking us to find the potential of the conductor. So the conductor itself is equipotential, so the question will not say find the potential at this point or that point in the side of the conductor. Every point in the conductor has the same potential. And find the potential also at point C, which is the center of the cavity. Here in such questions, if nothing has been said in the exam, we will assume that the metal is neutral. So first, let's just distribute the charges. So I'll have minus Q appearing on the inner surface, and because the metal is neutral, I have plus Q. Appearing on the outer surface, that will be uniformly distributed. So whenever you want to write the potential at any point in any question, you have to calculate the potential due to everything present in the question. So here that includes the outer surface, the inner surface, the point charge, or even if any external charges were present, even that should be included. Here in this type of question, we know the fact that the potential due to the inner charge and the inner surface will be zero everywhere outside the cavity, and the conducting material is outside the cavity. So therefore, in this conducting material, the potential will only be due to the outer surface, and the outer surface is behaving like a uniformly charged hollow sphere whose potential is something that we know. So the potential of the conductor will simply be KQ by the radius of the outer sphere. Alright, now for part 2, find the potential at point C. So potential at point C has to be due to everything once again. So it will be due to the outer surface, that will again be KQ by R. Due to the outer surface, potential everywhere is inside is a constant, plus due to the point charge KQ by R by 8, plus due to the inner surface charges. Now the inner surface charges at the center will produce a potential of K times minus Q by R by 4. Now how did I write this? If you have a hollow sphere where the distribution is non-uniform. There is one point where you can still write the potential, which is at the center, because every dq charge on the surface of a hollow sphere is at a distance capital R. So I can write potential as k dq by r, and when I integrate, it doesn't matter whether the charge is uniform or non-uniformly distributed, it will come out to be kq by r. So in this case, at point C, it will be k, the charge is on the inner surface is minus q divided by the radius is r by 4. And you will get your potential as 5 kq by r. So this is the potential at C. Now let's come to the concept of earthing. So earthing means that you're basically connecting any object to the ground or to earth, and we consider earth to be at zero potential. Earth can be treated as a almost neutral sphere, although its surface is slightly negatively charged, but earth can be considered as a neutral sphere. So overall we can assume its potential to be zero. So the potential of any object that is connected to earth, that potential also becomes zero. So that is what is known as earthing. So let's take a look at what kind of a question can come. So suppose I have three hollow spheres, concentric, metal spheres, so they are all conductors. Let's say I have charge Q on the inner sphere. Let's say sphere A, sphere B and C. Let's say the radius is R1, R2 and R3. And now I earth sphere B and I connect sphere A to sphere C. So once I close the switch and connect A to C, and of course B is earthed, I want to find the final charges on each sphere. Alright, so the way to do this question is we are going to assume, let's say that charge X flows from A to C. So A will have Q minus X, sphere C will have X. And let's say the final charge on B is Y. See, now this, when I say charge on B is Y, that means the total charge on B is Y. Now B has inner surface as well as outer surface. C also has some inner surface and outer surface. But we are not concerned with the charge distribution on each individual sphere. The only thing that matters here is the total charge on each sphere. And the reason is that suppose I have a sphere here, a spherical shell, thin spherical shell, and let's say the charge on the inner surface is Q1, charge on the outer surface is Q2. Suppose I want to write the potential at a distance R. The potential would be K Q1 by R plus K Q2 by R. Which is nothing but K Q1 plus Q2 by R. Eventually only the net charge will appear. And because the radii of the inner and the outer surface are also approximately same, the thickness is negligible. So even interior, the potential will simply be K Q1 by the radius plus K Q2 by the radius, which will basically end up being Q1 plus Q2 by the radius. So ultimately only the net charge will appear in all the potential calculations. So that's why we don't have to distribute the charge. If you distribute the charge before doing any calculations, you'll end up with many surfaces. Like each sphere will have inner and outer surface, two surfaces. So it will be like each sphere will be basically like two hollow spheres. So we don't want to increase our calculation, and we don't have to. So in such questions, do not distribute the charge initially. Take the variables as the total charge on each individual spherical shell. Alright, so first thing I'm going to do is I'm going to write the potential of B as 0. So if potential of B is 0, potential of B due to everything. So due to sphere A, the center of sphere A is at a distance of R2 from sphere B, from the surface of B. So the potential due to sphere A would be K into Q minus X by R2. What about potential of sphere B due to itself? That will simply be K into charge of B divided by R2. What about potential of B due to sphere C? Now sphere B is in the interior of sphere C. So in the interior of sphere C, everywhere the potential is going to be K times charge of C divided by the radius of C. and this should be 0. So this is one equation that we have. And the next thing is that because we've connected sphere A and sphere C by a metal wire, that means their potential will become equal, because remember, a conductor is equipotential, metal is equipotential. So sphere A and sphere C will become equipotential. So I can write potential of A should be equal to potential of C. Now what will be potential of A? Potential of A will be, due to itself, it will be KQ minus X by the radius of A. Due to B, KY divided by R2, because A is in the interior of B. And due to C, once again A is in the interior of C, so K times charge of C is X divided by R3. This is the potential of A. And what about potential of C? Due to A, C is at a distance of R3 from the center of A, so K times charge of A divided by R3. C is again at a distance of R3 from the center of B, so Ky by R3 for the potential of C due to B, and due to itself finally Kx by R3. This is my second equation. So these are two equations and two unknowns that you have X and Y. Once you get X, of course, you can get the total charge on A and C. So I hope you've understood how we can get the final charges on each sphere. Suppose you want to find the final charges on each surface of each sphere as well. So first you do this calculation, get the value of X and Y. Then you can distribute the charges. Let me just do that on the next page. So if we had Q minus X on the surface of A. Now there is no charge inside the inside A, so therefore all the charge on A will only appear on the outer surface. Now negative of that will be induced on the inner surface of B. That is what we saw as the property of conductor. Total charge on B is Y. So on the outer surface of B will appear Y plus Q minus X. Once again, the negative of this will appear on the inner surface of C. And now the total charge on C is X. So therefore on the outer surface I will have Y plus Q. You can see that the total charge on C would be equal to X. Total charge on B would be equal to Y. So once I get the value of X and Y, then it's very easy to distribute. So once again I am repeating, do not distribute the charges before doing the calculations. Do it at the end. That will be the quickest way to do such type of questions. Now let's do another question. So I have a sphere A, which is metal sphere A, which is given charge Q, and I have a metal sphere B, which is initially neutral, and this sphere is connected by a long wire to sphere A via a switch, which is initially open. And then sphere B is concentrically placed inside a spherical shell C. So the radius of sphere B and sphere A is R, and the inner surface radius of C is 2R and the outer surface radius is 3R. And the spherical shell C is connected to Earth. So the question is asking, find the final charges after this switch is closed. And this metal wire is just connecting directly B and A without any contact with C. So give it a try, then you can take a look at my solution. Okay, so let's take a look at how we can solve this question. So once again I have been given two information, which is that C is earthed, so that will be one equation, and because the switch is closed, the potential of B and A have to be equal, so that will be another equation. So I should have two equations. So let's say X charge flows from A to B. So B will have charge X and A will have charge Q minus X. And what about C? Now because the spherical shell C has different radius for the inner surface and outer surface, it will be useful for us to write down the charges on the inner surface and outer surface individually and then treat them as individual hollow spheres. So on the inner surface I will have minus X, and let's say on the outer surface I will have some charge Y. So the total charge of C would of course be Y minus X. Now one equation that I have to write is that the potential of C is 0. Now potential of C will be due to the charge on the outer surface Y, the charge on the inner surface minus X, and charge on the sphere B, which is again X. The potential due to A will be negligible on B and C because we've been given that the wire is a long wire. So that is the meaning of this long wire, that we have to make that approximation that the potential of A will be negligible at B and C. Alright, so when I write potential of C is 0, basically potential of the conducting material of C is 0. Now we've already seen in when we started conductors that see, B is like the charge inside the cavity of C. So the charge X and minus X will produce 0 potential everywhere outside the cavity. This red portion is my cavity for C. X is like the charge placed inside and minus X is the charge induced on the inner surface. So their resultant potential everywhere outside the cavity will be 0. So their potential in the conducting material of C will be 0. So the only potential will be due to Y. And because the potential of C has to be 0, that simply means that Y also has to be 0. Alright, now we have only left with one variable X, and we only need to write one equation, which is basically equating the potential of B and A. So let's do that. So potential of A is very straightforward to write. Potential of A will be only due to itself because B and C are very far away from A. So potential of A will be simply KQ minus X divided by its radius R. Should be equal to potential of B. A potential of B due to itself would be Kx by R, and there will be another potential due to minus X. So due to minus X would be K times minus X divided by the radius of the inner surface of C, which is 2R. This entire thing is the potential of B. This is potential of A. So just equate and you will get X as 2Q by 3. So therefore sphere B will have charge 2Q by 3, sphere A will obviously have charge Q by 3, and sphere C will have minus 2Q by 3 on the inner surface. So that's how we'll solve this question. I hope you've understood how we wrote down the equation for earthing as well as connecting B and A. Let's come to parallel plates. So if I have a system of parallel plates here, any system, any number of parallel plates, one thing that we have to remember is, suppose the charge on this surface is X, the charge on the opposite surface would be minus X, and this is just by Gauss law, because if you consider a Gaussian surface this way, because these blue sides here are inside the metal plate, the field there is 0, so the flux is 0, and therefore the total charge enclosed should also be 0. So therefore X and minus X will result in 0. Similarly, if I have Y and minus Y, that will also be 0, Z and minus Z, and so on. So can you see that if I add up all the charges, I will only be left with the outer charges of the outermost plates. Everything else will add up to be 0. So and these charges on the outer surface of the outermost plates have to be equal, so that they will cancel out the field inside each plate. So we are assuming long plates, so we can use the field due to an infinite sheet here. So for example, the field here due to the left hand side, due to this W charge, would be sigma would be W by area by 2 epsilon naught. Sigma by 2 epsilon naught is the field due to an infinite sheet, and that should be cancelled out by this charge, and therefore they have, these two charges have to be equal. The rest of the inner surface charges are anyway cancelling out the field in each metal plate. And therefore you can see that the value of W will simply be the total charge of the entire system divided by 2. So this is something that we should remember, and this will make our calculations very easy. So for example, if I have, let's say, 4 plates, and if I give charges Q, 2Q, 3Q, let's say 4Q. Alright, and now I want to distribute the charges. So the total charge, how much is that? 10Q. So I'll have 5Q and 5Q on the outer surface of the outermost plates. Now the total charge on the leftmost plate, first plate is Q, so I should have minus 4Q here. Negative of that should appear on the second plate, 4Q. Total charge is 2Q. So this charge should be minus 2Q. Negative of that here is 2Q. Total charge is 3Q. This should be Q. And the negative of that is minus Q. And you can just confirm that 5Q minus Q is still the total charge on the rightmost plate, 4Q. So I hope you've understood how to quickly distribute the charges on a system of plates. First step is always to write the outermost charge on the outermost plate using this expression. Now let's look at what happens when we earth a parallel plate system. So the concept here is, as many plates as you have, it doesn't matter, earth any one of the plates or any 2 plates earth at least, if you add earth at least one plate, what will happen is the field will become 0 outside. And the reason for this is because you earth, suppose this plate, the potential becomes 0. At infinity also potential is 0, and because a single plate is considered as a pair of parallel sheets, the field due to a parallel sheet is uniform everywhere. So let's say suppose this distance is d, and this is of course infinity. And let's say the field here is E1. So can I write E1 times d plus the electric field here is E times infinity should be 0. So you should clearly see that E itself has to be 0. So that the product of E into infinity will tend to a finite value of E1 into d. So the field outside the system of plates will be 0 according to this equation if you earth any one of the plates of the system. And because the field outside is only due to the charges on the outer surface of the outermost plates, because inner surface charges ka field will cancel out outside. Suppose I have x and minus x, their fields will obviously cancel out everywhere here and everywhere here. So outside the plates, the field will only be due to the outer surface charges, which is W. That implies W itself is 0. So whenever you earth a plate, the conclusion is that you will have 0 charge on the outer surface of the outermost plates. Whichever plate you earth doesn't matter. So let's take a question. So suppose I have let's say 4 plates. Let's say I have charge Q here. Let's say plate A, B, C and D. And let's say I earth both A and C, and then I connect B and D. So initially D is neutral. I want to find the final charges, and maybe we'll find the final charge distribution also on each plate. So here we don't need the value of the initial charge on A and C, because finally when they are earthed, that will determine the charges on A and C. Initial charge won't matter for A and C. Initial charge for B and D will matter because their total charge has to be conserved before and after closing the switch. They are not physically connected to earth or any other plate. And let's say the distance between consecutive plates are equal. Alright, now let's close the switch. So now because at least one plate is earthed, here 2 plates are earthed, the outer surface of the outermost plates of plate A and D will be 0. Alright, now let's assign some charges. So let's say on the left surface of B is X, on the right surface of B is Y, and let's say on the inner surface of D is Z. You can take any other variable also. You can take maybe on the inner surface of A is X, it doesn't matter. So in terms of X, I'll have minus X on the inner surface of A, and similarly minus Y on the left surface of C, and minus Z on the right surface of C, because of this presence of Z on the inner surface of D. Alright, so first thing that we need to do is realize that A and C are connected. So potential of A is equal to potential of C, and therefore the field here has to be equal because the distance is equal. Distance from B to A and B to C are equal, so the field has to be equal, so that the potential difference between B and A and B and C are also equal. And because the field here is equal, therefore X and Y also has to be equal. Because what is the field near a plate? The field near a conducting plate or conductor is sigma by epsilon naught. And sigma is charge per unit area. So because the field EAB and EBC have to be equal, X and Y also have to be equal. So we immediately get that X and Y have to be equal. Similarly, because B and D are also at the same potential, therefore the field EBC going from B to C and EDC going from D to C also have to be equal, because the distance between B and C and D and C are equal. And therefore, once again, minus Y and minus Z also have to be equal, or you can say Y and Z have to be equal. And that just makes it very easy. X is equal to Y equal to Z. And how will I find this value? The total charge on B and D should be Q. So what is the total charge on B and D? X plus Y plus Z. So I'll basically have X plus Y plus Z is equal to Q, and they are all equal, so each of them is equal to Q by 3. So my final charge distribution would be 0 minus Q by 3, Q by 3, q by 3, minus q by 3, minus q by 3, q by 3 and 0. This will be my final charge distribution. Alright, let's do one problem for you to practice on. Alright, so in this question I have A, B, C, D, 4 metal plates, and the distance between A and B and C and D are D, but the distance between B and C is 2D. And A and C are connected to earth, and B and D will be connected by a switch. The question is asking find the final charges after the switch is closed on each plate, and you can even distribute the charges. And initially B has charge Q and D is neutral. So give it a try, then you can take a look at my solution. Alright, now once the switch has been closed and we know that A and C are earth, so I'll have 0 charge on the outer surface on the outermost plates. Now let's say charge on the inner surfaces of B is on the left surface of B is X, this is Y. Let's say charge on the inner surface of D is Z. So I'll have minus X on the inner surface of A, minus Y on the left surface of B, and minus Z on the right surface of C. Now I need to find this. So first, potential of A is equal to potential of C because they are both connected to each other. And therefore, see, potential is nothing but electric field into distance. The magnitude of the potential difference is nothing but electric field into distance. So I should write electric field between B to A times D should be equal to electric field from B to C times 2D. So electric field from B to A is proportional to X, and electric field from B to C is proportional to Y. So X is equal to 2Y, that is one relation that I have. Similarly, because B and D are connected, the electric field from B to C and electric field from D to C will be related by the fact that potential of B and D are equal. So electric field from B to C times 2D should be equal to electric field from D to C times D. Now electric field from B to C is proportional to Y, and electric field from D to C is proportional to Z. So basically I have X is equal to 2, Y is equal to Z. That is my relation. And how will I find each value? I know that the total charge on B and D has to be equal to Q. So what is the total charge on B and D? That's X plus Y plus Z. Is equal to Q. And I know X and Y are both equal to 2Y. So Y will simply be equal to Q by 4. And therefore X and Z would be equal to Q by 2. Y should be equal to Q by 5. So X and Z will therefore be 2Q by 5. So now you can just substitute these values of X, Y and Z at the plates and get the total charges on the plates. I'll leave that calculation up to you. So I hope you've understood how to solve such complicated looking problems. They're not really complicated if you follow the process for such system of plates. Another way to do this kind of question is after you've studied the chapter of capacitance, you can actually draw the capacitance circuit for this system and solve the capacitance circuit and then get the charges on each plate. Personally, I find this the quickest way instead of having to first draw the entire capacitance circuit. So whatever you're comfortable with, go ahead. I personally find this the best method. Now let's look at a case where you have parallel plates but in the presence of an external field. So this is something that is not very familiar to students usually. So let's say I have two plates and I have an external field. Let's say I have charge Q on one plate and 3Q on the other plate. So here can I use the earlier expression that the charge on the outermost surface of the plate should be total charge by 2? No, I cannot, because I have an external field here which is being produced by some charge distribution, of course. So that charge also has to be taken into account. So the best way to do this question is realize that a uniform electric field can be produced by another plate. So if I have a plate whose total charge is, let's say, Q, we don't care about the distribution, but the total charge on this is Q. What will be the field? That will simply be Q by area. Let's say area of each side is A, divided by 2 epsilon naught. Sigma by 2 epsilon naught is the field due to a sheet. If this is not very clear, just imagine you have Q1 and Q2. So basically you have two sheets, Q1 and Q2. So the field would be Q1 by area divided by 2 epsilon naught plus Q2 by area divided by 2 epsilon naught. Sigma by 2 epsilon naught is the field due to a sheet. Each sheet has an area A here. This will be nothing but Q1 plus Q2 by 2A epsilon naught, which is nothing but Q by A divided by 2 epsilon naught. So now it's very straightforward. Basically, this system is equivalent to having an additional plate. And that plate has a charge Q whose value is equal to 2A epsilon naught E. So of course they should give you the area. So here the plates, let's say, have a side of area A. And now if the question asks you to find the total charge distribution, now it's very straightforward. The charge here and here would be Q plus 4Q divided by 2, Q plus 4Q divided by 2, and then it's very straightforward. The charge here would be 3Q minus Q plus 4Q by 2 because the total charge is 3Q, and the charge on the right side of this plate would be simply negative of this minus 3Q, and the total charge on this plate has to be Q. So from there you can simply get this is Q minus Q plus 4Q by 2 minus 3Q. You can do the calculation on your own. So I hope you've understood how we can get the charges on each side of each plate in the presence of an external field. Now let's come to a topic that is not usually familiar to students: accelerated conductors. So suppose, let me start off with an example of, suppose I have a square plate whose thickness is small compared to the other two sides. Let's say it's accelerated with A. So physically what is going to happen is, if you go in the frame of the plate, the electrons will experience a pseudo force to the left. I'm just drawing this front on view. So electrons will accelerate to the left and accumulate on the left surface. So I'll have negative charges here, leaving positive charges here. So in steady state, the free electrons will also acquire the same acceleration as that of the metal plate, and therefore if I have the electron accelerating to the right, you should have an electric field acting on it to the left, which will be produced by this charge separation. So how much will be the magnitude of the electric field? I'll have E times E as the force to the right on the free electron, should be equal to mass of the electron times A. So the electric field that will be generated is MA by E. So this is the electric field that will be generated inside this square plate when it's accelerated. Actually, it need not even be a square. It's just, let me say, it's a large plate. Large means the thickness is small compared to the area of the face, or the side lengths of the face. Alright, so what can we say about the charge distribution? We already saw that the charge distribution, charge density is epsilon naught dE by dx, if you remember. And here, because we have a uniform electric field, the charge density will simply be 0. So there is no charge residing in the volume of this conductor. However, we will have charge on the surface of the conductor. So can I get that charge? So let's say sigma and minus sigma are the surface charge density. So once again, this is simply like two sheets. So we know the field between two sheets, sigma and minus sigma. The field here will simply be, due to sigma will be sigma 2 epsilon naught to the left, and due to minus sigma will also be to sigma by 2 epsilon magnitude also to the left. And this should be nothing but MA by E, and therefore I'll get sigma as MA epsilon naught by E. So this is the surface charge densities that will be induced on the surface of the plate because of the acceleration. So one thing that we have to realize is, we started off this chapter on, or rather this topic on conductors, by stating that the electric field inside a conducting material will be 0. But remember, that condition was for only equilibrium. Here the electrons are not in equilibrium, they are accelerating. So that condition will not be true anymore. We have an electric field inside the conductor right now, as you can see. And let's finally look at another example of a rotating or rather accelerating conductor. So I'm taking the case of a rotating cylinder. So rotating metal cylinder, long, so the question is asking us, let's say first of all, find the electric field as a function of r. We are assuming steady state where the electron is also rotating with the same angular velocity as the cylinder. So that should be very straightforward. If I consider an electron here, I've been given the mass of electron is m. So if I consider the electron, the electric field that will be generated inside due to some charge separation will be towards the circumference, will be radially outwards, the electric field, so that the force on the electron is towards the axis to provide the centripetal acceleration. So my electric field will be radially outwards. The force will be, of course, inwards, E times E. That should be equal to m omega square r. So I'll have a variable electric field here, which is dependent on r. They could even ask you find the potential difference between the axis and the outer boundary. That potential difference between the axis and the outer boundary of the cylinder will simply be integral E dr 0 to r. So that will simply be m omega square r square by 2e. This radius is r. So you basically can see that rotating a cylinder can produce a potential difference between the axis and the outer boundary. Another thing that can be asked is the find the charge density. Now there are kind of two ways to do this. So we saw how to write charge in terms of the electric field. We saw it here, this expression, rho is epsilon naught by a d phi by dx. We did it for a spherical Gaussian surface, and when I was talking about this, I told you that we'll look at an example in accelerated conductor. So we're going to do that now. Here we have in our particular question we have a cylinder. So just keep this expression in mind. So we have rho is epsilon naught by a d phi by dx. So here d phi by dx would be dr, and what will be a? A will be the area of the Gaussian surfaces that we will consider, which will be cylinders now. So let me take the length of the cylinder to be L. So can I write area will simply be 2 pi RL, and the flux through this would be electric field times 2 pi RL, and therefore my charge density would be epsilon naught by 2 pi RL times d by dr of electric field times 2 pi RL. So 2 pi L will cancel out, of course, so I'll have epsilon naught by r d by dr of electric field is m omega square r by e times r. So very straightforward, simply r square ka derivative is what is required here. So what you will get is 2m omega square epsilon naught by e. So this will be the charge density here, and you should be able to see that this is a uniform charge density. So like I said, there are kind of two ways to get this charge density. One of them is by using the expression we found for the charge in terms of the electric field. The other is if you recognize that electric field is simply linear function of r, proportional to r, and that is what appears in the field for a uniformly charged solid cylinder. So if you realize that, then you will immediately be able to say that the charge density has to be uniform, and then you can simply use Gauss law to get the charge density. But if you don't, then you should be able to do it the way we have done it here. So you can see this is a uniformly charged solid cylinder. That is what's happening in the rotating cylinder, and it's all positive. That makes sense because the electric field required is in the radially outward direction. So the cylinder is all positively charged. But this should give you a question in your mind that if we started with a neutral cylinder and if we started rotating it, how does it become positively charged? Charge has to be conserved, of course, correct? So what is happening is that in the volume, this is volume charge density, in the volume it's all positive charge. That means the electrons have gone to the circumference or to the outer boundary of the cylinder. So that means there must be some surface charge density on the outer surface of the cylinder. So let's take that. So let's take a look at that. So let's say the charge density on the outer surface is sigma, and we already know that inside the bulk the volume charge density is a constant. We already found that out. So I can just write that the conductor total is neutral, so I should have rho into pi r square L plus sigma into 2 pi RL should be equal to 0, and therefore you can get sigma in terms of the charge density that we already found out on the previous page. And you can see sigma will have to be negative because rho is positive. That basically means that some electrons have gone to the outermost surface, leaving behind positive charge inside the volume of the cylinder. And that's it for today. See you at the top. Good night.